So what we are going to do is another example in our notes, so your notes should be out, but I wanted you to at least kind of compare some of those. I will give you real quick though, if you add H2 it should shift right, if you add NH3 it should shift left. And then on the back, if you add I2 it should shift to the right, if you add HI it'll shift to the left. So that should let you know if you're on the right path. So finish that up, fix that for tomorrow, and I'll check that tomorrow. So right now I'm going to do a different example with you than the demo. All right, I'm going to actually steal one from the homework. So we're going to go H2 gas plus I2 gas, reversible arrow, meaning reversible reaction, yields 2HI gas. And here's the bad joke. This is a very friendly reaction.
What's so funny about that?
It says hi.
Okay.
All right, so write the reaction down. That's an equilibrium reaction. I'm going to write a question down, and you answer it. Here we go. If the concentration of I2 gas, are we good here? You're having a rough day, huh?
You know, I was having a good day until, I would say about 8:05.
8:05, yep. So after this question, I'll show you why I have this set up, and it'll hopefully help you understand even more. So here we go. If the concentration of I2 gas is decreased, okay, so this time, instead of adding something, we're going to take something out. So if we decrease, so again, use your analogy here with the seesaw, right? You take something off one side, it's going to go up in the air, right? We can't have that. It's got to be balanced. So if we remove some I2, the concentration of I2 is decreased. Explain what happens to the, and I'm going to use those brackets here, the H2 concentration and the, sorry, it's that bracket, and the HI concentration. So if we remove some I2, explain what happens to the H2 concentration and the HI concentration. When I say explain, what I suggest you do is figure out which way the equilibrium shifts. Then you can explain why the H2 increases or H2 decreases. And the same thing for HI. I'm going to walk around and read what some of you wrote. Give you a couple minutes. So again, we're removing some of the I. That disrupts the equilibrium. It's stressed, so it's going to shift to adjust to go back to being at equilibrium. If you were watching me explain the demo, using this thing, hopefully you have a fighting chance here. If you get it wrong, that's okay. We'll go over it. And then I'll use this again up here to kind of hopefully hammer home the concept. So go ahead, take a couple minutes here, answer this. I'll walk around. Moving all over the place with this class. Either there, there, to there, to there. Like the utility guy.
The utility guy sitting down?
Mm-hmm.
That's pretty
Utility guy chemistry class.
pretty low.
And if you haven't made your Earth Day pledge yet, I got them up here. Make your pledges. Very simple things you can do. Oh, sorry. That's not really, I mean, that's okay. I don't buy it. Daily, little things you can do on a daily basis is probably better.
Yeah, I'm not going to shower for a month.
I'm not gonna sleep for 3 months to show my dedication to this.
I'm gonna destroy every gas car.
If they give me free one,
I'm gonna burn all the fossil fuels at once to get rid of them for good.
Can you answer this question, please? I feel like you have not answered it.
I don't really know the answer, that's why.
Yeah, because you're not trying today. Get your head out of your rear end and pay attention. I see Blake is conserving paper. That's how he's saving the earth.
Me too.
See, I know it's going every which way. On the
People
paper.
that don't conserve paper, I will fight them.
What was that?
Tell me why. Okay, some of you guys are writing
let me explain
what's going on, but you're not telling me why.
I think the H2.
So, Evan, if we remove the I2, right? Everyone look up here. Here's our balanced equation, our equilibrium equation. So our concentrations are constant, okay? If I remove I, so imagine there's a little bit of H2 sitting right here, a little I2 sitting here, HI. So I knock I2 right off. What happens to this? Think again. Think of a seesaw. You're sitting here, Xavier's sitting here. Let's say you're about the same weight. You jump off. What's going to happen? So what's going to happen to your side? I don't know. Think of a seesaw. You're sitting here, Xavier's sitting here. You jump off of this. What's going to happen? Yes. This is what happens. Everyone stop talking, pay attention. If you're talking, stop. Okay. This side is lighter now because we remove I2. That's not balanced. It's not equilibrium. So Evan, I'm still with you. So how can we get this side to go back down?
Put Evan back on.
The analogy with you and Xavier breaks down now. That's only to help you get started. Now you need to kind of think of it in terms of here. So you have a whole bunch of reactants, a whole bunch of products. You remove some of the reactants, so this side becomes lighter, like a seesaw. Does that make sense? If it comes out good. So now we can either take more reactants and put them over here, or we can take more products and put them over here. Right. So what direction are we shifting? Left. So we take our products, shift to the left so that it can become balanced again. So the answer to this question I haven't answered yet, but we should write down, what do I keep doing with this thing? Here it is. It shifts to the left. So the equilibrium, I want you to write this down, equilibrium shifts left. I've seen students use their pens or pencils on a Regents exam with this type of question. That's not cheating. You can do it. That's fine. Do whatever you can to help you answer the questions. I've seen them. They're sitting there and they're doing this and they're doing this. It really helps, but you have to understand how seesaws work. If you take something off, it's going to go up. If I put something on, it's going to go down. Then go from there. That's just to start the thought process. Then you have to kind of know what you're talking about. So we're here. Some of the products must break down, HI, must break down and produce more I and H, I2 and H2. So the part I have trouble as a teacher really expressing and getting across to my students is anytime we shift this way, you're making more of that. You're making less of this. The only way we can shift this way in a real chemical equation is if the products form more reactants. The reactants come from the products. So if you're making more of those, you have to be using this up. Okay? You have to be. They don't just appear magically. This breaks down, so the concentration of this will decrease. Both of these will actually start to increase in concentration if we keep removing I2. So if we remove enough I2, it becomes really, 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 really light. So then more of this has to be produced. More of this has to produce more of this, therefore to go back to being balanced. So the answer to the question is your H2 will increase in concentration because you're putting more of it. This will decrease in concentration. You have to use this to make more of it. That's the answer. But the explanation is because it shifts to the left. So let me write the answer. So H2 concentration will increase and the HI concentration will decrease. And again, that's because we're shifting to the left. We're going this way. we're going this way. Questions? Yes?
Are we supposed to write what happens when we take I away, or what needs to happen?
So, good question. I know exactly what you're asking. Good question. So, you're answering the aftermath. So, something happens. What happens after that? So, we take the I away. It gets all screwed up. Then what happens? So, don't think of it, okay, we're removing the I and then this is the shift. That's not the shift. That's what the stress causes. The shift is this way to go back to being balanced. So to answer your question, always answer all equilibrium questions from the second perspective. How does it shift to go back to being balanced? Does that help answer your question? Okay. Any other questions on this? We're going to do another example. I'm going to use this to help, hopefully help. It is not easy at first, but once you finally see it and get it, you won't forget it. All right. So let's say we have a reaction where we put all our reactants on the product side. All our reactants on the reactant side here. So we have reactants, we don't have any products. So our reactant side is heavy. How do we reach equilibrium?
We gotta react, right?
We gotta react. So which way do we shift?
To the right.
To the right. I have to take two of these, put them over here, and now we're balanced, which is equilibrium. That's a very simple example. I don't want to screw this up. I wrote it down. So now, if we take one of these from the product side, okay, and we put it on the reactant side, we disrupted equilibrium. We stressed it out. There's still a product here, but now we have too many reactants. How do we go back to being balanced? So we added some reactants, right? We now have to shift which way?
The right.
The right again. We shift some more back over here. Okay? So that's balanced. If it's not balanced, whichever way it's not balanced, you have to think about which way it needs to shift to go back to being balanced. Now, what if we add 4 of these little ones over here? And 4 of these really little baby weights here.
Yeah, it looks like a fan.
This a little bit, yeah.
You should all hang them onto one.
Zach, thanks for letting me borrow your weights. All right. So we have couldn't resist. So we have all the weights over here now. Now, stay with me. We're gonna take 2 of the family, the little adolescents here, put them over here, and we're gonna take 2 of Zach's weights, put them over here. Okay. And since it's balanced,
it's the way they're set up.
I know. Since they're balanced fairly well, we say that's equilibrium. Again, the analogy isn't perfect, but just go with me. So this is equilibrium. If we disrupt that equilibrium and we remove one of the middle-sized weights from the product side, what do we have to do?
Put a middle-sized weight.
Some of the reactants have to do what? React and form products. So I take one of the little baby ones, put it over here, and it's back to being balanced. So why am I showing you this? To help you give you another visual. I took something from this side, so it was like this. So I had to take a weight from this side. In reaction terms, we're reacting, forming products to go back to being balanced. So the gist of this, and we are going to write it down in our notes, but the notes I really don't think help too much. It's practice that helps. If we take something away, we always shift towards that to replace what we took. If we add something, it doesn't matter which side. If we add something to this side, it always shifts away from that because you added too much. So again, if we add some here, it shifts this way. If we add some here, it shifts this way. If I remove some, it shifts to fill it back up. If I remove some, it shifts to fill it back up. So I'm hoping this is making a little more sense. I'm going to write down what I just said, and then we're going to move on and try and learn about temperature. So this worksheet, again, you're going to be kind of doing the add, the remove, the add, the remove. That's this. And then the temperature questions, hopefully you'll have a fighting chance by the end of class. So we still got about 10 minutes. So I'm going to erase this. I'll write down what I just said, and then I'll talk about temperature. All right?
Mr. McCoy.
Yes?
Didn't you take one of the medium-sized ones off of this side, right?
Yeah.
Then you put a little one over here.
Right. So
What the heck?
the medium one's 20 grams.
Yeah.
So so it was balanced, right?
Yeah.
So I took the 20 grams here. Half of 20 is 10. So I took a 10 and put it over here, so that's really like 10 and 10. So if I took a 20 off and put it here, this is 20 too heavy, and that's 20 too light. So if I take 10 and put 10, now we're 10 and 10. Yeah, good question. When I was doing this a couple years ago, I set this thing up and I was writing it down. I couldn't get that right away. I'm like, how come I can't get this to balance? I kept moving a 20 and a 20, and it was like, it was a stupid mistake. So I understand if you don't think about it right away, you can miss that. All right, so write this down, please. If the concentration of the reactants is increased, equilibrium shifts. All right, I know it's a lot of me talking, and some days that's just how it goes, I know. But who was paying attention? If we add a bunch of reactants, which way does it shift? Towards the reactants or towards the products? Towards the products. Who is that? Jay, good. I hope other people are with me on that. If the concentration of reactants is increased, equilibrium shifts towards products. That should make sense. If you add more reactants, you're going to get more products. Right? I mean, I always think of peanut butter and jelly for some reason. If I have a lot of bread, a lot of peanut butter, a lot of jelly, I can make a lot of sandwiches. If I don't have a lot of bread, I don't have a lot of jelly, I don't have a lot of peanut butter, I can't make a lot of sandwiches. So the more materials I have, right, the more products I can make. So that just makes sense, even though this is confusing to some of you probably, which I understand. If you really think of it as like a big picture idea, if you add reactants, you're going to get more products. Where are the products? That way. All right, and then the opposite is true. If the concentration of the reactants decrease, if the concentration of reactants decrease, so this time we're removing some reactants. The concentration of reactants decrease, the equilibrium will shift towards what? So if we remove some reactants, are we shifting towards the reactants or towards the products? This one's harder to understand. That's why we use a meter stick or a pen or a pencil or your arm or your finger or whatever. Okay? So if you're a little confused here, let's do it. Steph, if I remove some reactants, what's going to happen? This side's going to go up because it's lighter, right? Think of a seesaw, right? So if I took all these weights off, this side's going to go up. Okay? So Bree, which way do we shift to go back to equilibrium? To the left. We shift some of the products to the reactants to be balanced, so we shift towards reactants. And on the regents or a test, you can say reactants or left, or you can say products or right. It's the same thing. Doesn't matter. Doesn't matter. So, I know there's probably still some confusion. Redo your homework or try and fix the ones you were confused about using what you learned today. We'll go over it tomorrow. There is another worksheet I'm going to be giving you tomorrow as well, so more practice. But let me teach you about temperature now, last 7 minutes or so. I'm going to show you part of the video, but I'm going to pause it and explain some things. What else did I want to tell you? Oh, matter and energy review packet due Friday. Separate paper, don't forget. I sent the text out. I have not written it up there, but don't forget that. Your quiz and lab tomorrow and Friday, don't forget that. I think that was it. Yeah, so lights please, Bree. Let me start the video, then I'm going to pause it, explain a little bit. And Jenny, come on up up real quick, Devin, Steph? I just have stuff to get back to you. I don't want to keep forgetting. I got enough stuff up here. Oh, sorry. It's a review assignment with the answers from Friday. Last Friday. All right, here we go. I'll give you a warning. The girl's voice is kind of weird.
Yeah, why you always pick people with weird voices?
Yeah, I don't know. The animation is good, so that's why I pick it. I basically, I don't pay attention to voices. I just pay attention to animation. And most of the time, I will just watch this with the sound off. I just want to see what the animation is.
That's how I'm not a weird person.
Animation like that, so.
What'd you say?
No.
Something really sexist.
We really should hire somebody with a good sounding voice to do these.
Like,
Denzel Washington.
I was thinking more like Morgan Freeman.
I mean, well, Denzel's. He's pretty
Who was
simple.
Darth Vader's voice?
Denzel.
You guys would know. What's that guy's name?
I might understand.
Really deep voice. Holy crap! I can picture his face. Anyways, here we go.
In this lesson, you will learn about how a system at equilibrium responds to changes in temperature. Le Chatelier's principle states that a chemical system at equilibrium always works to restore equilibrium.
So again, good animation. If we add a whole bunch of reactants, look what happens. It's disrupted. So what has to happen? Which way does it shift? Some of it has to shift on the right. Yes. You good, Shelby?
Yeah.
Good. You probably
This is
put that
James
away
Earl
for me,
Jones.
please. What?
James Earl Jones.
Yes. Did you look that up?
Nope. He's the guy from House of Barbecue.
I'd like to throw this right at me.
When it is stressed. To consider what happens to a system at equilibrium when temperature is changed, you must first consider the energetics of the reaction in question. If the forward reaction is exothermic, then the reverse reaction must be endothermic. Let's examine this hypothetical reaction.
If you don't understand what she just said, that's a problem, so I'm going to explain it. So, exothermic, heat goes on the right. You should know that from earlier in the year. Yes, you know school is cumulative, right? So things you learn at the beginning of the year, we got to apply at the end. So we learned a while ago, heat on the right, exothermic, negative delta H. So the forward reaction is exothermic, but the reverse would be endothermic. So if you had a potential energy diagram, it would look like this. A would be up here, B would be down here. This here, I'm really trying to break this. This would be our delta H. If you start at A, react, and end up at B, the product, that's a negative delta H. But if you start here and work your way backwards, you're gaining energy that's positive. That's what she means. So if it's this way being exo, that way is going to be endo. It has to be. You can't be exo both ways. That's impossible. So that's what she meant. Okay?
Where reactant A reacts with reactant B to produce product C and product D with a change in heat of minus 75 kilojoules.
She got all weird right there.
Very
It kind of
weird.
freaks me out. I get like the hair on the back of my neck like she's a ghost or something. I don't know, demon. So, totally weird. But, so this is exothermic. So I know I used A and B. She used A, B, and C, D. I can change it so you don't get confused. So if we have A plus B yields C plus D and heat, okay? So it's negative 75. So remember, if we were writing it in the equation, this would be right here. 75 would be over here. Okay. So here's the deal. If we increase the temperature on this system at equilibrium, I'm going to let her explain it, but we explain it differently, so I'm going to go first. If we increase the temperature, so here's our balanced equation, A, B, C, D with our heat. There's only one requirement I want you to assume with me. Let's assume heat is an actual product. So heat is sitting on this meter stick. This is like killing me here. A, B, C, D plus heat. If we increase the temperature, that's kind of like adding more heat. So if we add more heat to this side, how is this going to look different? Good. Jake's with me. I hope all of you are with me. If I add heat here, this side goes down because I'm adding more here. Does that make sense? With the seesaw analogy, stay with me. So if this is the stress put on the system, how does it shift to go back to equilibrium? To the left. So what she is going to say is kind of a general statement. She's going to say if you heat up an exothermic reaction, it always favors shifting to the left, which is the endothermic direction. It's confusing. All I want you to understand is find the heat and treat it like a substance. So if you add more heat, this is what happens, so it shifts this way to go back to being equilibrium. Endothermic, the heat's on this side. If we heat this up, it looks like that. It's going to shift to the right to go back to being equilibrium. So the way I teach it is I treat it just like concentration, except it's heat. So instead of adding more D and C, I'm adding heat. That's all it is. It's the same. So what I just spent all period talking about is the same exact thing. The way she words it a little different. Why am I showing it? Sometimes students pick up different things from different people. Maybe you learn it better this way. I don't know. So I'm going to play it for a little bit. Then we're going to end class here. All right? So just stay with me for another minute. Please don't pack up. Pay attention.
This means that when the forward reaction occurs, 75 kilojoules of energy is released and 75 kilojoules is absorbed when the reverse reaction occurs. So an increase in temperature would mean that the endothermic reaction would be favored to remove the excess heat.
So in other words, if we heat it up, it's going to shift this way. That's what she means by endothermic favor.
Therefore counteracting the imposed stress.
Stay with
Decreasing the
me, watch.
temperature would cause the system to produce more energy. Therefore, the exothermic reaction would be favored.
So
The dimerization of nitrogen.
the way she explains it is if you decrease the temperature, so look up here, we're here. If you have your heat sitting right here and we decrease temp, it's like taking heat off. So this side's lighter now. So now we're going to favor this direction. It's going to go to the right if you decrease the temperature on this. That's basically what she said. I'm going to stop it there. There is another part we'll watch tomorrow. Don't forget to do the same worksheet do today, but just the extra problems. And I have a meeting after school, so that's it.
Yeah, but it doesn't give you the. Here, I got a pen back. Just for
Yeah.
the homework.
Yes.
How do we know what side the heat is on?
The right side, every side.
It should show you
Is that the?
the 22K count.
Oh, okay.
Yep. What was I gonna say? Steph, did you get the notes?
Yeah.
Okay. Yeah, can you turn that on?